Alright, this time I'll talk about the problem Bessie Come Home. In this problem, previously we've done some problems involving finding the shortest path but without different lengths. But here there are paths with different lengths, and there's also a typical kind where there are two main methods of finding the shortest path. So here, although it's all in characters, but we know that in C++, the characters can be converted into ASCII codes, which are integers. So we don't need to worry about converting characters or anything. So here's my code. There's actually two ways to do it. So first, here's my main method, and I created two arrays. This is a 2D array consisting from the lowercase z plus 1. So as I said, C++ will automatically convert this lowercase z into ASCII code. So it will turn into a number, and then we can increase that by 1 just to make sure it's everything's in range. And if you check the ASCII code, the lowercase letters come after the uppercase letters. So I just put the lowercase z here, which is the maximum that we will get. And this distance will keep track of all the distance from z to every of the pastures. And I also created this visited array, which we will later use. So while reading the input, this thing had me for a while because I didn't notice that there can be multiple paths from pasture A to pasture B, but you just really need to find the smallest paths from them. You don't need to consider the bigger ones. You can just take the smaller ones. So every time you read this d, which is the distance from pasture A to pasture B, you have to compare it first. If it's greater than our current distance, for example, if we've already previously read one from pasture A to pasture B, we need to see if this one is smaller. If it is smaller, then we will set pasture A to pasture B and pasture B to pasture A, because the cows can walk in both directions, and they will be equal. The distance between them will be equal to d. And here's the two algorithms. The Floyd algorithm I've talked about from last video. This one's much simpler, but it takes O(n) to the power of 3. And the other algorithm, which is called the Dijkstra algorithm, takes only O(n) squared time. This is because the Floyd algorithm will find the minimum distance between every pair, but we really just need the minimum distance from every pasture to z. So we don't really need to find that much pair, but since it's only from uppercase A to lowercase z, there are barely any, the range isn't very big, so we can still use this O(n) cube time to find it. And this code is much easier to write compared to the Dijkstra algorithm. But I also have a Dijkstra algorithm here, which I made here. So in this algorithm, we will take use of the visited array. First of all, I set this distance z to 0 because we know that the barn is at z and we want all the cows to go to z. So in order to go from uppercase z to uppercase z, we know that we don't need to make any moves, so this distance will be 0. And then this is because from uppercase z to lowercase a, during these two intervals, there are a few of the extra characters that are not used in this program, so I'll just set them to visited, so later on we don't have to loop through them. And then here I find the current minimum distance. So this one, using the minimum distance, we will later use that so then we can add on to our current graph length and find a minimum distance for other from x to other pastures. So this is the minimum distance function. It will loop from a to uppercase a to lowercase z and find the index with the minimum distance and return it. And also I gotta check that the array that pasture isn't visited yet, because if it's visited, we would have already found the minimum distance, so we don't need to go through that again. And this is just in case if this returns -1, this means we've already searched through all the minimum distance. Because I set the default here to -1, then we will stop this loop. And otherwise, we will set that minimum distance node to 1, meaning that we visited that. And now we create a second loop inside here, also from uppercase A to lowercase z. And this is the part where we will update each of the distance and find the smaller ones. So first I check if x is not equal to y, because we don't really need to find the distance from the same pasture to itself. And we also need to check if we didn't visit y yet, because if we've already visited y, and if we want to find the distance again, it will just be a loop forever. And then here this is the part where we compare the distance. This distance y is the current distance of each of these pastures. And if there is a pass, so in the beginning here, I set everything to infinite. And this infinite is just defined here. This is, if you print this out, this is just a bit over 1 to the power of 9. And that, I didn't want it to use int max, because if we do this, this will make it overflow and we'll have a negative number. So I'll just use this infinite. So then if we add infinite by infinite, we will still have a number that's in the range of int. So here first it compares if the current node x plus the distance of the path from pasture x to pasture y. And we check if this is smaller than our current distance to pasture y. If it is, then we'll update the smallest distance to pasture y to the distance to pasture x plus the distance from x to y. And then this will keep on going until we visit all the pastures. And then we will have to use the distance array and find the smallest one from uppercase A to uppercase y. Here we don't need to search through the lowercase letters, because it's stated in the problem that there will be cows only exist in the uppercase letter pastures, and we don't need to search pasture y, because we don't need to search pasture z, because that is the barn. And also here's the Floyd algorithm. In case you haven't seen it, this is just a triple loop, and the first k, this loop, it will choose a node that is in between I to j. If there's a path from I to k to j, and then we will compare this with the current path from I to j. And notice, if there is no path from I to k, or there's no path from k to j, there will be one of them will have the infinite value, so it will make sure that these two add together will be smaller than the gij, and this is why I used the infinite. You can also set it to -1 if you want, but then that will take some more if to check the function. And here I will be the starting pasture and j will be the ending pasture. So here we compare if the path from I to k plus the path from k to j is smaller than the path from I to j. This means that it's taking another route using the k pasture. You will have a smaller distance than taking the route directly from I to j. So if that's smaller, we will set gij and gji, because remember, the cows can move in both directions, and we will set them equal to the smaller one, which is gik plus gkj. And then finally here, just to make it compatible with our final loop that checks for the minimum distance. I use this loop from uppercase A to uppercase Y, and I set all the distance. I set every distance I into G, Z, I. This is because we've looped through everything, we've already found the shortest distance between every pair. So here we'll set it to the shortest distance between Z and passenger I. And this will also, after use this function, it will return, and then we can also print out the final answer using this loop.